Greetings everyone, Dr. Doherty from Abilene Christian University. Let's think for a little bit about what it means to have velocity and acceleration. So velocity, by definition, is a change in position with a change in time. So if I draw a number line and I measure the position of this gray object, if the velocity is 0, that position doesn't change at all. Now, whenever that position changes, whenever the object moves, I have to have a velocity, and how much velocity just means how fast is it moving. So if I give this yellow guy some velocity, there it goes. Now, when the velocity is constant, that does a fixed amount of distance per time. So this is like moving at exactly 10 miles per hour or 1 meter per second. And if we watch this go again, you see that that speed never changes. Remember that the speed is the magnitude of the velocity vector. So the velocity vector is the speed going at a certain direction. So my velocity here would be 10 miles per hour to the right, or 1 meter per second to the right, or whatever speed that actually happens to be. But now let's see what happens when I give it some acceleration. So the acceleration is going to make the velocity change. So if I am in a car and I start at rest and I am later going 60 miles per hour, I have accelerated from 0 miles per hour to 60 miles per hour. And that takes me some amount of time to do, and the measure of that change in velocity over a change in time gives us an acceleration. Acceleration is also a vector, and it can point the same way as velocity or a different way from velocity. So let's watch the green ball now. So here, I start out at rest. My acceleration vector is pointing to the right. So my velocity keeps speeding up, going faster and faster to the right. I start at rest, and after a few seconds of travel, I'm moving pretty quickly. Now acceleration can also mean to slow down. So in this case, if the acceleration vector and the velocity vector point in opposite directions. So here we've got, it's moving to the right really fast, but it's accelerating to the left. So as more time progresses, it gets slower and slower and slower until it actually stops. Now if we can compare all these together, so I've arranged all of these to race from start to finish, but they'll take exactly 3 seconds. Just watch this for a couple of times. Look at the different motions. See how these things move differently between constant velocity yellow, speeding up green, and slowing down red. So 0 acceleration, positive acceleration, and negative acceleration. And one more time. All right, now a really great way to visualize this or to play with it is to go and use a set of computer simulations called PhET, the Physics Educational I forget what it stands for. It's an amazing project from University of Colorado at Boulder that has simulations for lots of fields of math and science. I use it all the time, and you should too. Let's go take a look at a simulation they call Moving Man and see what it does. Welcome to the Moving Man. So, our sophisticated fellow standing here in a number line at x equals 0 in the middle. I've got x equals positive 10 to the right, negative 10 to the left. I can control him by clicking and dragging on him, but let's start off on the slider bars. So I can set his position anywhere I want. So if I put him somewhere at, say, about x equals 3 meters, and I click play, nothing happens. The velocity is 0, the acceleration is 0. Velocity means a changing position, and when that's 0, the position just doesn't change. So let's reset this. Now if I want to turn on velocity, let's click this box to see our velocity vectors. I can have him going to the right or to the left, and the longer the vector is, the more velocity he has. So that is, the faster he's going to go. So for example, let's start all the way over here at negative 10, and let's do a velocity of, say, 5 meters per second. So I can figure out what's going to happen. I'm going to have to travel 10 20 meters to get to this other wall here. I'm going to do 20 meters at 5 meters per second. So that should take me, let's see, about 4 seconds to go. Let's click play and see what happens. All right, he is completely unfazed. So as I move him around, you can see that when we're going slowly, the velocity vector is very slow. When I move him fast, the velocity vector gets pretty large. So we can control this any way that we want. The negative velocity or a positive velocity. Let's reset this now and let's try some acceleration. We'll start off on the left. I'll start off with a velocity of 0. And now let's do an acceleration of 1. Now you could actually go and use the kinematics equations to calculate how long it will take to go 20 meters with an initial velocity of 0 and an acceleration of 1. Let's click play and see what happens. So with my acceleration vector turned on, I've got this green arrow, and we could use our kinematics equations to calculate how long it takes to move 20 meters with 0 initial velocity and 1 meter per second of acceleration. But let's think about the picture and the motion. So if my red arrow is my velocity vector, it starts off as 0. Let's click play and watch it first, and then we'll go back in more detail and take a look at the pictures. We start off at rest, we speed up, we keep faster and faster until a glorious crash. So going back, velocity of 0, acceleration of 1. Now for every second that goes by, I'm adding my acceleration vector to my velocity vector. That is, I'm adding the green arrow to the red arrow. So let's watch this and pause with every second. So here at 1 second, my velocity is going to be 1 meter per second. At 2 seconds, it's 2 meters per second. At 3 seconds, it's about 3 meters per second. My acceleration vector is not changing here, but as we click play, the red arrow gets longer and longer as it moves until it crashes. Now we can play all sorts of games that we want. So for instance, let's click pause here. Let's do a positive velocity, but a negative acceleration. So if my velocity is, say, 6 and my acceleration is -2, I know that when I start at time 0, I'm moving at 6 meters per second. 1 second later, I will have slowed down by 2, so my velocity is 4. Another second later, my velocity is 2. Another second later, my velocity is 0. It'll take me 3 seconds to stop. And then I'm still accelerating to the left. So I'm going to turn around now and come back the other way. And smack. Keep playing with the moving man. You can, of course, turn off the sound or delete these walls entirely until you get a feel for how this works. So to summarize what we've learned, acceleration shows how the velocity changes in time. So here, if I've got a positive acceleration vector and my velocity starts as 0, I can think about I take my velocity vector, and for every second that goes by, I add an acceleration vector to it. You should see the video on graphical vector addition if you want to think about this in pictures. So at 0 seconds, we're at rest, but at 1 second, I've accelerated by 9 kilometers per hour, and at 2 seconds, I've accelerated by another 9 kilometers per hour, and for every second that goes by, my velocity gets bigger and bigger to the right. I'm speeding up as we move along. Acceleration can also be for slowing down. So here, if my velocity is pointing to the right, but my acceleration is to the left, see that it's -5 meters per second. For every second that goes by, I add this vector to my velocity vector. So my velocity vector gets slower and slower and slower until eventually it stops. To summarize all of these in graphical form, let's think now about if I were to make some diagrams of position, velocity, and acceleration versus time. These diagrams are really powerful ways of showing compactly exactly what happened to something. There's a ton of information here, and it's really worth some effort getting used to reading these and interpreting them. But the best way to do it is to play in a physics lab. So let's take a look. Here I have an object that starts at some x value and it never moves. It's a pretty boring thing to watch. So if I plot its position versus time, it starts at some x initial. Let's say it's sitting on a number line at x equals 2 meters, and it's always sitting there at x equals 2 meters forever and ever and ever. So remember here, my vertical axis is position, my horizontal axis is time, and when x doesn't change, I get this boring horizontal line. What's my velocity? Well, it's 0. Is it always 0? Yep. So my velocity is just 0 forever, my acceleration is 0 forever because my velocity is never changing. So now let's throw in a constant velocity. So I've got an object that's moving to the right, let's say at 1 meter per second, and it's always moving at 1 meter per second. So when I look at my graph of position versus time, for every second that goes by, I'm moving 1 extra meter. And that moving an extra meter, that's really giving me a slope to this line that's not 0. So if you remember, a horizontal line has a slope of 0. A line that's going up to the right has a slope that's positive. A line that's going down to the right has a negative slope. So as I'm moving here with a positive velocity, my line now has a positive slope. So every second that goes by, my position is increasing. Now this is just summarized by the equation that we have for our kinematics equations. Final x is initial x plus velocity times time. If I think about what my velocity is doing, well, it's a constant. So it's, say, 1 meter per second, and it's never changing. So this is just a flat horizontal line. And my acceleration is 0 everywhere because my velocity never changes. All right, so finally, now let's picture in our head something moving with constant acceleration. So here, I start slow and I speed up as time progresses. Now, the big 4 equations of kinematics tell us what happens to the position when it's moving with velocity and acceleration. And that has this 1/2 at squared. That gives us a parabola. Now what's happening here is when I start out, my slope is my initial velocity, like it was here. But because my velocity is changing, my slope is changing everywhere, so I get this curved shape. So notice the difference in position. When I'm not moving, it's a horizontal line. When I have a constant velocity, it's a straight line where the slope is my velocity. But when I'm accelerating, my line is curved. So the acceleration gives us curvature. For velocity, my velocity is always changing. In this problem, I'm always speeding up. So I start at one velocity. At some time later, I'm at another velocity. Well, that change in velocity with the change in time, that's the definition of acceleration. So here, the slope of this line is just my acceleration. When my acceleration was up here before, my slope was 0 because my acceleration was 0. If I'm speeding up, I've got a positive acceleration, a positive slope. If I'm slowing down, I've got a negative acceleration, a negative slope. Finally here, my acceleration is constant but not 0, so it's not changing in time. We can also look at the moving man charts just to verify these results. So again, if I click play with no velocity and no acceleration, let's set a position somewhere. Well, my position is a horizontal flat line. My velocity and my acceleration are 0 everywhere. Now if I start back at -10, but I do a positive velocity, as we go for a little bit, I see now that my position is a line with a positive slope, a slope of exactly 2. My velocity, though, is now a horizontal line sitting at 2 meters per second, and my acceleration is still 0. As I reset this one more time, we'll do a position. Let's do a velocity of 0, and let's do an acceleration of 1. So as I click play here and we watch what happens, now my position is curved because the slope is the velocity and the velocity is always changing. My velocity is now a straight line with the slope of the acceleration, and my acceleration is 1 and not 0. So as our last example, if I do a demonstration that we did before, I start on the left. I have a positive velocity of 6 and a negative acceleration of 2. Pause this video and think about what the graph's going to look like. All right, let's see if you're right. Okay, so what happened? My graph is curved, so I know it's accelerating. It's curved downward, so I know the acceleration is negative. You see this point right here where I stopped and turned around? So my position was getting more and more positive, and then it went to go more and more negative. This would be where I stopped and turned around. What's happening here? Well, if I go down, my velocity is a straight line with a negative slope. So again, that means I have a negative acceleration. And this moment here where my velocity crosses 0, that's the moment where I stop. Because when I'm stopped, my velocity is 0. And this is where we stop to turn around. But because my acceleration is still negative, my velocity started to go negative, so I started moving to the left. So here with a positive velocity, I'm moving to the right. When my velocity is 0, I'm stopped. When my velocity is negative, I'm moving to the left. Here my acceleration was negative to everywhere until I smacked into the wall at 6 seconds and we came to a sudden abrupt halt. So think about these. Think about the objects that we saw move. Think about the moving man simulation from PhET. And really get used to when you see an equation or a graph or you think about velocity or acceleration, get really used to connecting these equations or these concepts to the feeling of something actually moving in the real world. That's going to help you a lot.